My name is Youngjoo Chung at GIST Korea, and the title of my talk is Mathematics of Series using the Symbolic Computing Package. And I'm going to give a brief introduction of the package, and I'll show you some examples of using the package functions for manipulation and evaluation of mathematical expressions. My presentation is entitled Mathematics of Series with the Symbolic Computing Package. My name is Youngjoo Chung, and I'm from GIST Korea. The overview of my talk, I'm going to give you a brief introduction of the Symbolic Computing or SC package, overview and the brief history, and then I'll show you some of the functions that are used for the mathematics of a series, kernel and the package functions, and I'll show you some examples for using the functions in the package for these topics. And I chose these topics to show you that the mathematical as is not enough to evaluate these quantities, like definite integral shown here, and the residue, and the Fourier series, approximate solution of nonlinear ODE, and asymptotic behavior of the Airy functions AI and BI. Okay. Well, about the symbolic computing package. Well, the keywords of the package is the mathematical calculation, the computer-aided mathematics, and the symbolic and algebraic computation for handling mathematical expressions. The overview, let me make it a little bigger. Okay, well, this is an add-on pipe package that facilitates symbolic computation with mathematical expressions. Not everything, but especially for the mathematical expressions. And it has over 800 functions, and it has its own programming kind of a language. And it is used to display and the interpretation of various mathematical expressions, like derivatives, integrals, sums, vector operators, brackets, etc., using the traditional notation. So all these quantities are displayed using the traditional notation, but it is still in the standard form. It's not the traditional form, and the package has its own code for interpretation and the display of these quantities. Well, it was written by me. The motivation, it is to design and implement a symbolic computing system based on Mathematica that can manipulate the various mathematical expressions using traditional notation and the deferred on-demand evaluation. The difference, well, that occurs when you load the package is that some of the quantities, like the sums, integrals, products, etc., are not evaluated. And these quantities are evaluated by calling the function that starts with evaluate something. And there are some 20 or 30 functions to evaluate, okay, for evaluation of the expressions, and it is deferred on-demand evaluation. The objective is to replace handwritten calculation with symbolic computing and software-based automation. And the features, it allows traditional notation, algebraic manipulation, and etc. And it provides a powerful platform for streamlined manipulation of mathematical expressions. Okay, I'll show you some of the examples here. Before I go ahead, I load the package. Okay, all of the functions in the package start with SC, meaning symbolic computing. And for example, SC derivative expand, and then this is expanded. It's already, this is output. And SC transform derivative. So we have a second derivative of f, and this is the option for specification of transformation of variables. So the old variables are x and t, and new variables are x and eta, and then this is the transformed derivative. And since these integrals are not evaluated, these two integrals are merged automatically. And let's see back expand. This is a pretty complicated quantity. Call of this A and FB, these are all back functions. So A and B are vector functions. F is a scalar function. And if you expand it, then you have this result. And sequential execution of functions. SCMA function does this. And we can do navigation using the SCMF viewer palette, which is this. By the way, well, this is the palette for controlling the execution of the functions in the SCMA. So, so here we have an integral and a transient. This is a function for transformation of integral. And the transbar, this is the the old and the new variable. And x is a tangent t. And this is composition of functions. These are executed in the reverse order. So simplify, power expand, and the vector int. These are executed in the reverse order. And if you do that, then we have this result. And then, well, this, as you can see, this integral is not evaluated. Then I call SC eval int, then it is evaluated, and the result is given here. Well, extended composition of functions. Okay, we have a second order differential equation here, and this is the series form of the solution. And then put it in here, okay, and expand these derivatives. And here, well, again, this is a function composition. It's executed in the reverse order. So eval deriv with the prime means x derivative, and expand, factor, sum, and divide the result with x to r, and then put everything inside the sum, and then shift the variable in the sum. So if I execute it, well, there are about six functions. And if I do that, then this is the result. Okay. So this is the expansion of the differential equation in series. And then we can obtain the initial equation and the recurrent relation from this result. Okay, so this is the final form. And as you can see, this must be 0, and therefore we have a double root for r, 0. And this must be 0, and this is the recurrent relation. And if you solve it, then basically the equation is solved in series form. So advantages are very clear. So we have a close emulation of handwritten calculation, etc. And we have a good readability. Okay, the brief history. This was, well, development started about 15 years ago. And about 5 years of beta testing. And next month it is going to be released as a commercial product. This is a plan. We have a documentation, and I cannot show you the whole documentation, but this is the guide page of the package. And then here, this reference and index. These are the all list of functions in the package, and index of functions, etc. Okay, let me go back. Oops, I don't know how to go back. Oops. I'm not familiar with this. Yeah, on the right. Ah, I see. Where is it? Ah, I see. Okay. All right. Um, okay, the functions for series. Well, there are several corner and package functions associated with the series. And the series function expands, for example, this up to the second degree of x and y. But the problem is we have up to fourth order if x and y are small quantities. And this is Fourier trig series. And there's another function in the package, Taylor series. And xyt, this function expands up to the specified order for all variables. So it doesn't have like x squared, y squared, things like that. So we have only the second order for both x and y. And the power series gives an infinite series. So this is expanded first to this form, and then this is expanded using binomial series in this form. So this is a complete infinite series for this expression. And the power series supports all of these functions. There are tens of functions, and these functions can be expanded using the power series as an infinite series. Well, this shows an example of analysis. And, this is the result. Well, this is an analytical solution for small amplitude oscillation. And this is a numerical solution with no approximations. And you can see, well, for small oscillation, then you have to expand it to the first order in Taylor series. And here we have a function, and there are 6 variables. So if you use series, then you will have up to 6 order actually. But the Taylor series here, the package function expands only to the first order for all these variables. So you don't have to collect the terms that are only the first order, and it is done automatically by this function. Okay, I'll show you more examples. Evaluation of the definite integral. Well, this one looks very easy, but actually, well, this is the function. I found this problem in Quora, and direct integration does not work. Well, this is very simple, but integrate doesn't work. So expand this into a power series. Okay, then this exponential can be expanded. And you can see here how this is going to proceed. So, by the way, this is the palette to control the execution. And then this can be, well, you can evaluate it, but I transform again using this rule. T is equal to minus log x. Then it's transformed to this form. And again, well, this is going to be the integral for factorial function. This is n factorial. So, so this is cancelled. And then this is the final form. It is in series form, but it can be evaluated numerically. So this is the result. And this series converges pretty rapidly, as you can see. With the 10 terms, it is about order of 10 to minus 10. So it's very accurate and fast. Numerical integration using SC eval in nint gives the same result. Next one, evaluation of the residue. Well, this one it has a isolated singularity. And if you evaluate it using the system function, it doesn't evaluate. But using this definition again, and then doing the transformation and expanding into a power series, and combine the double sums, and then using this formula from the complex variable, then we have this result. Okay? So it is transformed to this integral, and this integral is expanded in series completely. This is infinite series. And here, okay. And this series, this is a double sum, and as is, it does not evaluate. If you call sum function as is, it does not evaluate. But if you convert it using this rule, using the here, n plus p is changed to n. And then n ranges from 0 to infinity, but p ranges from 0 to n. So this is a finite sum. To a finite sum like this. Then if you evaluate for p only, okay, p only, then we get this result. Okay, so this is a single sum in n, and this sum can be evaluated. And the result is written in terms of hypergeometric PFQ function. And this is the closed form expression, and we can evaluate the numerical value, and this is the result. We can compare it using numerical evaluation of this integral, and it gives the same result. Okay, evaluation of the Fourier series. Well, this is the question: what is the closed form for this Fourier series? This is a periodic function with a period of 2. Yeah, with a period of 2. And if you plot it using different number of terms, for example, with just one term, it is a cosine, 5 terms, 10 terms, and 20 terms. And you can see it is a periodic with a period of 2. And we can obtain, well, the result will be a polynomial between plus minus 1. And this sum can be actually evaluated. I tried it. So if I evaluate the sum, it is the first result is given in terms of a polylog function. But it doesn't give much insight about the behavior of the function. So I call function expand. If I do that, then this is the result. Then I do post-processing, call these 3 functions in series. Then the result is, surprisingly, it's very simple. It's given, so this is the closed form expression valid between plus minus 1. And it is periodic. So we know the function for all t. But alternatively, we can use the method of a Fourier series to derive the same expression. So I start with this, and if I evaluate the values for 0 and 1, then it is given by these. And these sums are, well, it's pretty neat. It's elementary, and these are the results. Then the differential equation, well, this is infinite cosine. And if you try to evaluate it, you will not, because this is infinite sum, and it is not convergent. But using the theory of a Fourier series, you can show that it is written in terms of a Dirac delta function. So this is the result. So this sum, even though this is a divergent, it is a singular function. And it has a singularity at t equals 2k minus 1. But otherwise, it's all 0. So we have result indicates that this is equal to pi square over 2. But the first derivative is discontinuous at the 2k minus 1. So the solution must be the solution of this differential equation using these boundary conditions. And this is the result. So we have obtained the same result. And if you plot ft, you can see it's exactly the same plot. I'm running out of time. Well, approximate solution of the nonlinear ODE. Well, the solution of a nonlinear ODE doesn't have a standard established procedure for solving the equations. So we have to do many trials and errors. And the leading behavior of the solution, it can be shown that it's given by this. And I skipped the derivation. And A is the location of the movable second order for singularity. And then if you assume the Laurent series for x sufficiently close to x equals A, so assume this series form and put it in the differential equation here. And this is a fairly complicated code for manipulation of this differential equation. And well, I'm not going to go through all this, but eventually I end up with the solutions for the A coefficients up to n equals 3. And the recursion relation is given by this. And then, okay, the recursion relation for n larger than or equal to 5, it is given by this. So if you know the value on the right side, the sum, it is where the terms are from a minus 1 up to a n minus 1, which are supposed to be all known, okay, using the recursion relation. And then using all these values, you can calculate the nth coefficient. So if you generate the coefficient for n up to 10, then you can see well, it's 0 to a1, and then this is the first non-vanishing coefficient, a3, a4, but here a4 is arbitrary. So we have a one constant of equation, and then a is also constant. It is a movable singularity, and therefore a and c are the two free parameters. And these are determined by the boundary conditions. So if you plot the series solution for different values of a and c, so a is this is the singularity. So if I move it, then, well, actually this is a solution of the series solution, and therefore it is it's convergent only within the radius of convergence, and outside it we don't know. Okay, so this is the series is restricted to the region of convergence, and the c, this is the second parameter, and the c is changed. Then by using manipulating a and the c, we can satisfy the boundary conditions, okay, two boundary conditions. And the plot of the numerical solution, well, this equation can be solved numerically using any solve value. And well, because there is a singularity, we have all these error messages. And let me turn them off. Okay, so here, this is a solution with the y0 equal to 0, and y prime 0 is also 0. But if I change the boundary condition, then we have a different solutions. And one of these solutions can be, yeah, it coincides with one of the solutions obtained using the series. But you can see on the negative axis, it's oscillatory. But this is outside the range of convergence, and therefore we do not see here. And analysis of the function in this area must be done using other methods for the asymptotic series. Okay, finally, let me go briefly over asymptotic behavior of Airy functions. This is the Airy equation, and this is the integral representation of AI. And then using the complex analysis, the stationary points are here and here, but use the stationary point in the upper half plane. We cannot use it. Okay? We cannot use it because this one, we have to go upwards. But there is a singularity here, so the result is not convergent. It's not convergent. Okay? It diverges, and therefore we cannot use it. But if you use this pole, not pole, but this point, the stationary point, and then let me go. Okay, and then using the Taylor expansion, and then take them out. Okay, and finally, the integral can be transformed to this form, and this is Gaussian and easily evaluated, and this is the result. For negative g, the stationary points are here and here. So we have to pick up the contributions from both stationary points. And if I do that, then this is more complicated. And the code for doing the analysis is given here. And if I execute it, so area I is when the g is negative, it is given by this term. And asymptotic series function, it returns the same result when the argument g is less than pi. So for g, which is not real negative, this is true for all complex g other than the real negative axis. It is given by this, and on the negative real axis, it is given by this. And the Airy bi it is more restricted. So for this condition, it's given here, and this for negative real axis is given by this. The full asymptotic expansions is given here. This is infinite sum, and this is the Wolfram symbol, and these are. Okay, so this is a full asymptotic expansion. As the asym series supports these functions. These are quite a lot, and these functions, the package, it knows the formula for the asymptotic expansion for these functions. So if I plot the Airy function with one term, you can see it's pretty accurate, but if you plot the error, it's quite significant. It's order of about 0.001. With the two terms, the error is very much reduced. 3 terms and 5 terms. So with more terms, it is very accurate for large x, but error increases for small x. And similarly for Airy bi, with 1 term, 2 terms, 3 terms, and 5 terms. Okay, that's all, and thank you for your attention.